Alright, here is a quick overview of how to derive the equation for the line of best fit from using calculus. So the problem setting, we had some data. We had some inputs that we said were x, and we had some outputs that we said were y. And we were trying to get an equation for a line that would fit that data. Like this. And we called it the line of best fit. This guy is the line of best fit. But why is he the best? Why is it the best? And the reason that we said this would be the best is if our criteria for bestness here is if it minimized these distances between it and the actual data. So we have data points that look like this. There's some x and y pair. And we're trying to write an equation that looks like y equals a plus bx. And I'll say I. To predict, given some x input variable, can we predict what y would be? All right, so this is what we want. We want an equation here. And again, the equation, the things on that line, what we're saying is the best equation is the one that finds them the least distance from the actual data. So we have this expression. These are going to be our predictions, and we actually know the actual values yi. So I'm going to actually just add this guy on there. So these are the predictions, and we're trying to minimize the distance between them and the actual data. So that would just be what the difference between the two are. Except that if we swap positions, like if one of the points is on top of the line and one of them is on the bottom, that would change this from positive to negative. And so to avoid that, we'll just square this and say this is in fact what we want to minimize. We want to minimize the distance between the actual and the predicted. And we'll be able to come up with an actual formula for this using calculus. Okay? But right now, there's nothing beyond just an equation of a line and a way to represent that distance. All right, so moving on from there, remember we had this, the actual minus the predicted. And we were saying we were going to square that distance. And we want to do that over the entire data. So we're going to sum these distance squared over every data point. And now this is what we actually, this expression is the thing that we end up trying to minimize as a function. And the way that we'll translate this is we say, well, this guy here is a prediction. It's a linear equation, so it looks like a plus bxi. So then we have an expression, or even better yet, a function in terms of a and b that is the sum from 1 to n of that difference, a plus bxi squared. And this now is where we unleash the calculus. Like we can minimize that expression pretty easily using calculus. So first, let's go ahead and minimize means take a derivative and set it equal to 0. This is a function in terms of two variables though, so we've got to take a derivative of each and set them equal to 0. So first we'll do derivative with respect to a. Okay, so I'll say f prime of a. And this is just a chain rule problem, and we have nice properties of the summation operator that allow us to just kind of treat it like it's a normal function here. So 2 times the sum of yi minus a minus bxi times the derivative with respect to a in here, which is -1. All right. And so we just have this -2, or we can bring the -2 out, and then we have a sum. So I'll write it like this: -2 times the sum of y of I And the sum of n a's is just going to be, well, all right, the sum of a and the sum of bxi, something like this. But I actually know how to add this up because there's no I here, so it's just going to be that however many data points a. So we can rewrite this as -2 sum of yi plus the sum of a is an plus 2 sum bxi. All right, but with just kind of a little rearranging here, I can solve for a. And what I'll get is, well, actually, let's go ahead and do that. So solve for a, I can say negative an equals the sum of yi plus the sum of b xi, and I've got this -2 out front here, so, or wherever I forgot to add it, so there it is. But now I can just go ahead and divide by negative n. These guys will just swap position if we care about that, but I get a equals, right, -1 over, well, in this case it would be +2 over n, the sum of yi, minus 2 over n, the sum of b xi. But if I add something up and divide by how many, all that in both of these, all that is an average. So I can rewrite a equals oh, wait a minute, and I forgot, actually, before I did this, I should have just set this is equal to 0, so we can divide that, we can get that 2 out of there. That was a factor of everything, so it will just divide out, and I don't know why I'm doing that. This is just, we can just have this as 1. Yeah, and then, so what I have are just averages. I've got this average of y, and I'll write that as y bar, minus this average of b, times x, right? So minus b x bar, and bingo, there's my first expression. Okay, there's an expression for a in terms of just the means of the data, and this lurker b, we've still got to deal with him. But we'll be able to do that pretty easily now, because we can just look back at our expression and substitute in this newfound value for a. All right. So, right, let's do that. We just found that a equaled y bar minus bx bar, right? And we had this expression that said the sum of y sub I minus a plus bxi squared. This was the thing that we were minimizing. But we can just go ahead and take back in here what we have for a. So now I can rewrite this expression as the sum of yi minus y bar minus bx bar, right? That guy, plus bxi. This thing squared. And just go on from there, right? So this ends up, I've got a b in both of these, so I can write this as the sum of yi minus y bar plus b times xi minus x bar. This whole thing squared. Yeah, and then we'll take the derivative, set it equal to 0, and solve. So again, all I've done here is just go revisit my original expression and pump back in what I found about A in order to only have it in terms of B's and things that we know. We know y bar, we know x bar, we know xi, we know yi, so I've only got one free variable here. It's just this B. So again, derivative would be 2 times the sum, etc. And what we should end up with is we end up finding that B is the sum of xi minus x bar times yi minus y bar all over x bar minus xi quantity squared. So your task is to show that derivation.